The droplet-based microfluidic synthesis for high-performance inks and coatings is revolutionizing material science by offering precise control over particle size, composition, and dispersion, leading to superior functional properties in printed electronics, biomedical devices, and industrial coatings. Traditional methods of ink and coating production often suffer from inconsistent particle distribution, aggregation, and inefficient mixing, which can lead to defects, poor adhesion, or reduced conductivity in applications like printed circuits or high-quality paints. But what if we could engineer each droplet to contain exactly the right balance of materials? In droplet-based microfluidics, tiny liquid droplets act as individual reaction vessels, ensuring uniform synthesis of nanoparticles or pigment formulations with controlled size and surface properties. This method is already being used to create conductive inks for flexible electronics, where silver or graphene nanoparticles are dispersed evenly, improving conductivity and durability. Another exciting example is the development of self-healing coatings, where microfluidic-generated capsules embedded in paints release repair agents when scratched, significantly extending the lifespan of protective surfaces. In the textile industry, water-repellent and antibacterial coatings produced via microfluidic synthesis are enhancing performance in outdoor gear and medical fabrics. Could this technology lead to eco-friendly, solvent-free inks that reduce industrial waste? What if microfluidics could produce biodegradable coatings that break down safely in the environment? As industries demand smarter, more sustainable materials, microfluidic droplet synthesis is emerging as a game changer, offering precision, efficiency, and innovation in advanced inks and coatings. Droplet-based microfluidics allows for precise control over the composition, structure, and properties of inks and coatings by manipulating fluid flow at the microscale. This method enables the production of highly uniform nanoparticles, polymers, and pigment dispersions with superior performance characteristics such as enhanced durability, conductivity, and optical properties. Compared to traditional bulk synthesis methods, microfluidic systems provide improved mixing efficiency, enabling better control over particle size, morphology, and chemical composition, which is crucial for applications in high-performance printing, electronics, and protective coatings. Microfluidic synthesis has been used to produce conductive inks for printed electronics with exceptionally uniform silver nanoparticle dispersions, ensuring higher conductivity and long-term stability in flexible circuit applications. This process is like crafting an artisanal espresso, precisely controlling temperature, pressure, and ingredient ratios to achieve the perfect blend and texture. The development of high-performance conductive inks relies on the precise formulation of metal or carbon-based nanoparticles. Microfluidic synthesis enables the production of monodisperse metal nanoparticle suspensions, coupe, silver, copper, or gold, that exhibit high electrical conductivity and excellent adhesion properties when printed on flexible substrates. This approach eliminates the common issues of particle agglomeration and uneven distribution found in conventional ink synthesis, ensuring smooth, defect-free deposition in printed electronic circuits and RFID tags. Researchers have developed graphene-based conductive inks using microfluidic processing, allowing the production of flexible, lightweight electronic devices, including wearable biosensors and smart textiles. These conductive inks function like meticulously woven fabric threads, creating seamless electrical pathways without weak spots or interruptions. Microfluidic synthesis enables the controlled formulation of inks with tailored rheological properties for 3D printing applications. By fine-tuning viscosity, surface tension, and curing kinetics, microfluidic engineered inks improve layer adhesion, structural integrity, and resolution in additive manufacturing. This capability is especially valuable in bioprinting, ceramic printing, and multi-material fabrication, where ink consistency is critical for building complex geometries with high fidelity. Microfluidic-based ceramic inks have been developed for high-precision 3D printing of dental implants and aerospace components, achieving superior mechanical strength and fine feature resolution. This method is like using a fine-tip calligraphy pen instead of a thick marker, offering greater precision and control over the final printed structure. Droplet-based microfluidics enables the synthesis of microcapsules and nanocarriers that release healing agents in response to environmental stimuli such as mechanical damage, pH changes, or temperature shifts. These smart coatings can autonomously repair scratches and cracks in protective films, automotive paints, and anti-corrosion layers. The microfluidic approach ensures uniformity in capsule size and shell composition, improving the efficiency and durability of self-healing coatings. Self-healing polymer coatings synthesized through microfluidics have been applied to aerospace components, extending service life by preventing microfractures that lead to structural failure. These coatings function like a biological wound healing system, automatically sealing damage before it worsens. Microfluidic synthesis allows for the incorporation of antimicrobial agents, such as silver or copper nanoparticles, into coatings that prevent bacterial growth on medical devices, food packaging, and high-tip surfaces. Additionally, hydrophobic coatings created using microfluidically generated nanostructures exhibit excellent water-repellent properties, making them ideal for anti-fogging applications in eyewear and windshields. The precision of microfluidic fabrication ensures consistent dispersion of active ingredients, enhancing the effectiveness and longevity of functional coatings. Hospital surfaces coated with microfluidic synthesized silver nanoparticle films show a significant reduction in bacterial colonization, reducing infection risks in healthcare settings. These coatings act like a rainproof jacket for surfaces, repelling By leveraging microfluidic techniques, scientists can engineer color-tunable and thermochromic inks that change color in response to temperature, UV exposure, or electrical fields. These dynamic inks use microfluidically synthesized liquid crystal droplets, or nanopigments, with controlled light-reflecting properties. Such materials are widely used in security printing, wearable technology, and responsive packaging. Thermochromic inks developed for food packaging indicate temperature fluctuations, ensuring that perishable goods remain within safe storage conditions. This is similar to mood rings, changing color in response to environmental conditions, providing real-time visual feedback. Microfluidics enables the production of high-performance transparent conductive coatings, which are essential for touchscreens, OLED displays, and solar panels. By precisely tuning the synthesis of indium tin oxide, ITO nanoparticles, silver nanowires, or graphene dispersions, researchers can create coatings that combine high electrical conductivity with optical transparency. These coatings provide an alternative to conventional vacuum-deposited films, offering lower-cost, scalable production methods. Flexible touchscreens using microfluidic synthesized silver nanowire coatings maintain high conductivity and transparency while offering enhanced mechanical flexibility. These coatings function like an invisible network of highways, conducting electricity while remaining optically clear for display applications. Microfluidic synthesis allows for the controlled development of UV-resistant coatings that protect surfaces from sunlight-induced degradation. Additionally, anti-smudge coatings containing microfluidically dispersed nanoparticles create oleophobic and hydrophobic barriers, preventing fingerprints and smudges on smartphone screens, eyeglasses, and camera lenses. The smartphone manufacturers integrate microfluidically engineered anti-smudge coatings, reducing the need for frequent cleaning while maintaining screen clarity. This is like applying an invisible shield to a device, keeping it spotless and resistant to wear over time. The transition of microfluidic synthesis from lab-scale to industrial-scale production holds enormous potential for the ink and coatings industry. Continuous flow microfluidic reactors enable high-throughput manufacturing of advanced materials with precise quality control. Further developments in automation and AI-driven process optimization are expected to enhance scalability, reducing costs, and making microfluidic-based inks and coatings commercially competitive with conventional materials. Industrial-scale microfluidic reactors are being developed to produce conductive inks for printed electronics, increasing manufacturing efficiency while reducing waste. Scaling up microfluidic ink production is like transitioning from handmade pottery to automated ceramic manufacturing, maintaining precision while enabling large-scale production.